Motors are in a ton of the electronics you touch in a day, and many that you don't. They're in your electronic toothbrush, they're in your ceiling fan, they're in your vacuum cleaner, robotic or otherwise. So motors control electronics everywhere, but what controls the motors? Here to talk about advancements in sensorless motor drives is Miguel Mendoza of Renesas, who's going to walk us through how some of the newest advancements in circuit-level design can change the way we use motor-driven products all over the world. Hello and welcome. My name is Kate Smith. I am the editor-in-chief of All About Circuits, and thank you for joining us today for this tech chat. Here with me today is Miguel Mendoza of Renesas Motor Control specifically, and today we're going to be talking about the RAJ306001 and RAJ36010 IC family for motor control across a bunch of different applications. Some really interesting ones coming up in this presentation, this conversation that we're going to be having. We've got power tools, we've got drones, we've got robotic vacuums. It's the whole slew of motor control applications to go through. Thank you so much for joining us today, Miguel.
Thank you, Kate, and hello, everyone.
All right, so let's get started because we have quite a bit to go through today. So let's start with the basic introduction of this particular system and package family.
So here it's what we call this, this family, motor control family. It's really highly integrated solution where we have the MCU integrated in the package as well as what we call the analog front end. So effectively, we have a system in the package. The only components that typically used outside is the MOSFETs, and that way the customer can set the appropriate, let's just say, on resistance depending on the power requirements and the voltage requirements. So this is pretty highly integrated products that typically are used where size constraints is important, and typically on like tools, drones, they have very small, say, workable area to put the hardware. So having a compact design is very important.
Yeah, of course. And that's a term that we come across a lot in the industry at this point, that highly integrated design. Can you tell us a little bit about why this is so beneficial aside from the footprint?
Well, the thing is that we added a lot of analog features already on the AFE to kind of like, let's just say, not burden the code. So for example, we have internal self-aligned dead time generator. So effectively, the customer doesn't have to worry about putting delays between the on time for the high side and the low side for the complementary half bridge. Usually that becomes a catastrophic failure if you have a cross conduction. And then, so it's easy to set, to the dead time, depending on how much margin you want with our device. So that's not something the customer has to worry about code. And then we're actively actually monitoring the gate drive voltage. So we know when that FET is on or off. So that way we have probably the best optimal case of as far as not losing energy to heat, when the current freewheels across the body diode of the MOSFET. So that's one feature. We have other features like slew rate control. So effectively what we've done is, we've taken some of the important analog parameters and we incorporate it into the AFE. So that way the customer doesn't have to worry about that. It just becomes a serial program that they just set a register, and that's it. They don't have to change resistors. They don't have to change caps or anything on the hardware. It's all pre-programmed and makes it super easy.
Calling these simply motor control ICs doesn't really describe the full capabilities of this product family.
You can see that how much processing power we have and how many IOs we have, 28 channels. So that way customers actually not only can drive the motor, but they could actually control the speed through one of the IO parts through, like, for example, potentiometer or a switch, or if they want to get some readouts, like, for example, you can put LEDs, in case you see overcurrent or if you see some faults. Or even like some customers have done is they've used it almost like a fuel gauge. So since we are monitoring the voltage, you could actually tell the customer, feedback to the customer that, the battery voltage is decaying at this level. So it's kind of like you can use it as a fuel gauge. And another kind of neat thing that I've seen customers use is, since we're monitoring the RPM and we're monitoring the voltage and the current, you can characterize those parameters. And like, for example, let's just say in a vacuum, if something blocks the air, the current's going to drop because there's no resistance or no air resistance, and the RPM is going to increase. So then this could tell the user, hey, sock's stuck in the hose. You don't want to operate that way because the motor's going to get really warm. So we should remove, or if the trash is full, something like that. So, and those are the since we have an MCU inside our device, customers can add their application, to into our device without adding an external microcontroller.
And that's kind of how these types of families evolve, right? Over time, is you guys release something really cool, the customer ends up using it in a way that maybe you didn't intend or expect, and then
Mhm.
the next iteration, that's part and parcel of the design, right?
Yeah, so the way I like to describe it is like, what we build is the canvas, and the customer can add their color and their their whatever design they want to with this. So, but what we provide is pretty much the engine to be able to drive the motor very efficiently, and then we have plenty of memory for the customer to utilize for their application later.
I like that very much, that concept of the canvas. And in fact, would you say that, looking at slide 4,
Hmm.
would you say that this is sort of the breadth of canvasi?
Yeah, yeah. So effectively, I mean, obviously we targeted the consumer market, and we treat power tools like a consumer market. Some people treat it as industrial, but so that was the number one focus. And then, but because we built it with that flexibility of having, that programmability, now we can address from the portable vacuum cleaners to like fuel pumps, ceiling fans, even blowers, vacuums, and even these like robotic vacuum cleaners and so on. So this is a very, what do they call it, a general purpose MC, a motor control solution. So it could be repurposed for many applications, and in each application will have its own, let's just say, constraints or difficulties. But we've seemed to been able to overcome, because each of those, let's just say, hurdles with this solution.
Right. And that's actually one of the really nice things about this conversation that we're having today is that we're going to dig into some of these application examples and look at the different design needs and the challenges that are associated with each one. So to set the stage a little bit, looking at these example applications, what do you think is the most important thing leading into this conversation? What's the unifying factor that we can sort of frame this conversation in? Obviously, motor control.
Yeah, yeah, that's the common denominator is motor controls. But let's just say battery operated is kind of the target. Let's just say that's the input power. Usually, what we're working with is battery. And when you're working with batteries, you only have so much finite power to work with.
Mhm.
So running motors efficiently as possible, and to maintain also the battery life as long as possible, or the increase the runtime. Those are the key goals that we've been focused on. That we've been focusing with our products.
Mhm.
Like, and then the other aspects is also try to reduce the cost to our customers. And here we have a power tool, and then the power tools have, obviously these are one of the early, let's just say, consumer products that jumped into brushes DC from brush motors. Historically, they used to be line voltage, and then they went to battery operated, but they were brush. But as brushes DC motors has become more, let's just say, ubiquitous, or or utilized more, and then the IC devices has become cheaper throughout throughout the decades. Now brushes DC is found a home in power tools. So now that instead of having the commutator that's mechanical, you have to have electronic commutator. But because you have an electronic commutator, you can adjust, let's just say, the phase to improve the efficiency over the RPM. Now, one of the biggest issues with let's just say a drill is that a drill has to operate at full torque with zero movement,
Mhm.
and so that's so you're going to have to draw a lot of current to be able to rotate the rotor. That's obviously it's tied to gears to give it more, the high torque ratio that you get from a drill. But we actually accomplished not only this very efficiently, but we actually accomplished it doing it sensorless. And so
Right.
we're one of the first, or one of the few, say, IC vendors that have provided a solution that could drive a drill sensorless. Typically the drills, they use Hall sensors, and that's to make, to detect the rotor position, and that's very important. You can't spin a brushless DC motor without knowing the rotor position, and but that adds costs. You have typically Hall sensors. I mean, there's a range for them, but let's just say like on high volume pricing, they're 10 cents. Plus, you have to have the PCB board, you have the mounting, and then you have to have a power management device to bias the LDOs. I mean, sorry, the Hall sensors. So you use like typically an LDO. So that adds cost to the customer, and we've been able to create algorithms that be able to detect the rotor position with very little movement of the rotor.
Can you tell us a little bit more about how you guys accomplished this? What were the challenges that you had to overcome for Renesas to be able to actively design this system?
Here we have kind of the scope shot of what kind of the processes that we're doing, and so typically, and everyone when they operate a motor sensorless, they have to they do what they call the inductive sense motor, which means you just add energy into the motor, and then that usually puts out, depending on the rotor position and the magnetic field, it gives you some kind of feedback to the custom, to the device. But what we have is the special secret sauce, which we call the MRI mode, or magnet rotor position identification. But this MRI mode, this is kind of our secret sauce, and so with the analog front end that we have in our device, so we have an obviously internal analog solution that has a very wide dynamic range. So even small movements in the energy field we can detect, and so we can kind of, like to say, educated guess where that rotor position is based on the just the energy that we pulse into the motor and what jumps back to us. And then what we do is we kind of educate decision, but we're pretty accurate to understand it. And then we excite the magnetic field with the simple 120-degree drive, or the other name is trapezoidal, and then just to move the rotor. And then as soon as the rotor moves, then we get what they call back EMF, or that's created by the rotor rotation. And then we can assure where that rotor position is, and then it becomes easy. So the real secret sauce is that one step, the step number two, that we can do that maybe our competitors can't do, because typically they use the internal op amps that are available in the MCU. The gain that doesn't have as much gain,
Mhm.
and then we have, obviously we have some circuitry that does the back EMF sensing that helps us with so with very low energy from the motor we can detect that rotor position, and that's something that we've accomplished. It took a lot of work, but we've I can actually show it working if you don't mind.
Oh, please do.
So actually, on the left we have the original drill, and on the right we have our solution, and obviously ours is sensorless, and then the original solution uses Hall sensors. So I'm going to play these videos simultaneously so we can kind of see how they kind of how they compare. So I apologize if it's going to get loud. We have an auger bit, and we're drilling through two plywoods, so it's the same condition. And as you see from the video, actually we're drilling a lot faster with our device. Now you can see our board; it's hanging on the drill, so it's not inside the motor, inside the chassis. It's like hanging right by the handle. But anyway, I'm gonna turn this off so we can talk. Um, but as you can see, we're actually drilling faster, and this is something that was interesting to us because we also did something that was very unique outside of what everyone's doing. And so we have this hybrid approach, what we call 150-degree drive.
Hmm.
And by running it at this 150-degree drive, we're actually running much closer to the motor characteristics. So effectively, we're getting a better a phase current, on a sine wave on the phase current. On the original drill, you can see on the left, and then we're going to zoom in to the phase current, and you can see how the phase current looks kind of more like a triangle shape as opposed to sine wave. That's what they call it, trapezoidal, because it's the shape for the phase current. On our solution, even though we're not using a vector, we're not using sinusoidal, we're still using based on the original 120-degree drive. But what we're doing is we're actually phasing or advancing the phase to the optimal level of the motor, and then we're getting a nice smoother sinusoid wave for the phase current, and that actually translates for us to be more efficient. So here we have a dyno test, and we're comparing the original drill with our drill. And what we saw over 20% improvement in horsepower for the same amount of torque, and that translates to higher RPM for the same amount of torque.
And that's being credited to is it the control algorithm? Is it the finer timing control? Is it the more more fine sensing of where the motor position is? What exactly is it
It's
that's
it's a mix. Actually, that's a really good question. It's a mix of software. Obviously, the software is key. I mean, if you're driving this and you're getting a sinusoidal phase current, so effectively, if you were to take a motor and you spun it and you put your scope probes on the just on the motor and make it work like a generator, you're gonna see a sine wave. Some motors, depending on the design, might be a little bit less sinusoidal. Maybe it's some weird shape, but for the most part, a good design will give you a sine wave, and you'll have three of them. The closer you drive a motor to that sine wave at that RPM, you're going to drive it with, not fighting, the motor. So that means you have less, torque ripple. You're going to drive it much more efficiently. So the software or the algorithm is key. I believe 15. I mean that's about 80% of an improvement that we got is through that, and the remaining improvement is through the other. Let's just say that the analog circuitry that we included. For example, our dead time is very short, so that way we're not freewheeling as long as you might, where you're losing energy to heat, because now you're conducting across the body diode of the MOSFET, and that translates to heat, and that's power loss. So that's one of them. The other thing is that our device could sync and source about 500 milliamps, so we could drive MOSFETs they have very low RES on and or on resistance, and then that's the other key. Those are the conduction losses. Some of their competitors they can only drive 250 milliamps or something like that. So working with MOSFETs with very low R on resistance, typically they have a very large input capacitance, and so you need to have a lot more sources to be able to drive more current. So to be able to turn them off and turn them on appropriately. And so our devices kind of has enough power to work with MOSFETs with like sub 1 million MOSFETs for motors switching at about 20 kilohertz PWM, which translates to like where you can drive almost 300 amps in a 20 volt motor application. So it's plenty of energy to overcome the input capacitance of the MOSFETs, of the low on resistant MOSFETs. Because you could use other MOSFETs that have high on resistance and they have low input capacitance, but then you're losing a lot of energy and heat, and then you got to put a bigger heat sink on the MOSFET, and that's cost. Heat metal is not cheap.
yeah. Well, and just to put a little bit of context in there,
Hmm.
when we're talking about losing this heat radiated into the environment, I mean, obviously, it's not going to be, you radiate a little bit of heat and your battery is dead immediately. But
Hmm.
what kind of scale are we looking at? How much can this shorten the lifespan of the battery of a device like this?
Well, actually, if we're going to talk about battery runtime, maybe we can look at an example where we took a very popular cordless vacuum cleaner. So in this example, here's pretty much an example what a 28 volt or a 6 cell driven vacuum cleaner. Now in this case, runtime is important. In the power tools, I would say customers don't say, "Oh yeah, we need to runtime," because it's typically you're using it for a few minutes, and then it's standing, it's sitting on the table, and then you can swap batteries. But in the
Mhm.
vacuum application, there you're working throughout the time, throughout the day, and or you want to get the work done, and that's it. You don't want to be swapping batteries and stuff like that. You just want to get the cleaning done, and then you can charge it after you're done. So runtime is key. What we've done is we took the motors and the battery, and then we kept everything the same except we replaced the original board with our prototyping board. We call it the PTP 5. We're just coming out with a new generation, which is the PTP 6, and these are what we use to do these kind of prototypes, kind of proof of concepts with our solution at these different applications. And the original solution, like we it was we had our apps engineer unfortunately had to sit through the lab, let the vacuum run for 43 minutes until the battery got to that level where it shut down, and then we had to reproduce it. And we saw that at the same RPM, same airflow, same everything at the normal mode. We improved it from 43 minutes and 50 seconds to 49 and 21 seconds.
Well,
Yeah, and then for the full boost mode, and this is where most people use their vacuums, because these little tiny motors, I mean, they're they're not, they consume about 250 watts at full speed, and then they get about maybe 22 CFM airflow, which is cubic feet per meter. So they try to, they run them real fast to try to, get enough air power, enough pressure to kind of do the work. And then so the runtime decreases dramatically, because now you're drawing a
mhm.
lot of energy from the battery pack. So in this case, the original one we measure is about 11 minutes and 41 seconds. And we improved it by 12 to 12 minutes, almost 13 minutes. So almost 2 minutes of additional work that you can do with the same charge.
Yeah, that makes a difference when you're designing consumer products like this, right?
Yeah, yeah. I mean, obviously, I don't want to be vacuuming for anywhere more than, say, 20 minutes or 30. But if you have to do it, right, you don't want to say, oh, now I lost charge. Now I don't get to finish. Now I got to, schedule
Hmm.
more time, right, to do it later.
Hmm.
Yeah.
Yeah,
So that's the key. I mean, for this particular market, that's the runtime is very critical. I think 20 minutes is kind of the holy grail for a cordless vacuum, if you could run it at full speed.
yeah, that makes sense, and that's obviously it translates directly to how your customers end up selling their own products, right?
Yeah, yeah. Actually, could I share something with you that I'm working on that's going to be disruptor? I mean, if
Please.
you're
Oh boy.
huh?
Oh boy. Yes, please do.
Okay. So the background comes that, I've been, many years back I was working on this ceiling fan for the India market, because they're moving from AC motor, power hungry ceiling fans to brushes DC, because you can run the ceiling fan at a third of the power. Now in India, they don't run the ceiling fans like we do here at slow speeds. They run them at 400 RPM. I'm talking about, it's like a guillotine in
Wow.
the ceiling and at full speed. But I was so impressed with Brush's DC motor, like that I could actually spin at same speed and by the way, keep the speed consistent, because there the voltage drops, and they don't necessarily have the most modern power grid. So this, and then the ceiling fan will always kind of track the voltage, because it's an AC motor, right? And
Mhm.
but with us, it stayed consistent, and it was just amazing. It's like, why not make an upright vacuum cleaner that, those are popular in the states, or even a canister vacuum cleaner, and then why not make it cordless? I mean, why? I mean, why have to plug it in? So,
Hmm.
for example, like comes from a parts warehouse. I just kind of I found like a common motor, and sure enough, these are AC 120-volt motors. They consume about 1100 watts, and the air power is pretty good. It's about 200 watts, and then this is from the model that I'm showing on the right. It's very popular. And so the idea that I had was, well, if I could run it with a brushless DC motor, I could, I assume one third of the power or something like that. But obviously, it's not that easy. So we did a proof of concept where we actually took that motor that I showed on this previous slide, and we put a brushless DC motor that had very close to the same RPM, and then we did a proof of concept, and wow, like it was close, it worked, but it wasn't, obviously it didn't match up to the same RPM. But about a
Mhm.
year ago, right before COVID, late February, beginning of March, I went to visit a partner, and I'll disclose who it is because I have the rights to. So I visited a partner by the name of Domel, and what they've done is within the year they provided us a brushless DC full size vacuum cleaner where I could actually make this industrialized. I can we can sell it in the millions. So what we've done is we retrofitted a canister vacuum cleaner with brushless DC, and obviously I was off by the power. The power improvement was about maybe a little bit over half for the same airflow, because
Wow.
just to give you comparison, we took an anemometer and we measured a very popular cordless vacuum cleaner. Remember I told you those little motors, they spin real fast to try to
Mhm.
so you can feel the airflow, you can hear but they're super loud. They're like a little jet engine because they're running 90,000 to 100k RPM, which is like, and they're only getting about 22, at least we measured 22.4 CFM airflow. With our motor inside the cavity with the HEPA filters and the other filters, just like the same testing, like just putting the testing unit in the nozzle, we're measuring very close to 7 CFM. So now you're really working. Now you're actually doing it. And if I may, I'm going to demonstrate this video, and so I did this narration, and I try to cut it down, but this is the brushes DC motor inside the vacuum, and then on the back side we put our board just to kind of show it. So let me demonstrate, and then we can discuss this a little bit.
Yeah.
There's so much suction that you can even feel how it sticks to the ground. Look at that carpet. Let's get pulled up. You'll see that I'm pulling this carpet that we have it for the front door. This heavy duty carpets, and I'm actually lifting it. It wasn't the bowling ball demo, but I'm gonna eventually, when I get hands on a bowling ball, I'm gonna try it. There is a pressure valve, so like if you do stop the suction, eventually the it releases air, so you're not overheating the motor. Because remember, it used to be a brush motor, and those get really hot. But the brushes DC, because they're more efficient, it doesn't really require that much cooling like you do with a brush motor.
That's awesome.
I feel that Renesas is different. It's like, we really, we want to help our customers be competitive, and instead of them telling us what they're doing, sometimes we'll give them ideas of what you can do with the technology. Since we have the benefit to build the device from the silicon up, we're not constrained to like designs that they have that they want to reuse because they don't want to focus on making changes to the inverter design or making changes to the MCU or the libraries. We can build it as we get these ideas, and we try to break some of the barriers, and then also bring in partners. Like for example, in this case, I partnered with a very what do they call it, a global supplier for vacuum motors, and I pitched it to them that I wanted a motor that's brushes DC for the full size vacuums. And sure enough, we built the partnership, and now we have the ability to sell it in the millions.
That's fantastic. It's not every day that you come across a situation where, the type of work that you guys are doing at Renesas here actually translates so directly to something that affects the consumer and device that distinctly. That's very cool to see.
Yeah, and then the other thing that also helps is by us going through the same hurdles that they're going to go through, right? Because they're going to have to deal with EMI, they're going to have to deal with parts availability, they're going to have to deal with size and everything. We go through that learning curve as well, and so now when we provide a solution, now we have firmware that we can offer customers. We can
Mhm.
offer them the layout, the Gerber files for the hardware, so they don't have to deal with. We already have optimized the BOM, the bill of materials, already, so we can have something that's very cost, that sensitive, for cost sensitive applications. So we've done a lot of the heavy lifting. So it does take a long time for us to kind of get something out because we're going through the hurdles. But when we have a conversation with the customer, now we're effectively reducing their design cycle because
Yeah.
we've done a lot of the heavy lifting in the beginning.
Yeah, that's pretty incredible, actually. So essentially, when you're talking about providing Gerber files and the BOM and everything to customers, are you guys kind of in the business of reference designs now? It's not
Yeah,
just
that's exactly what we're doing. It's a reference design. I mean, this is new. I mean, this is not something that was typical from Renesas. Actually, I've been championing this idea
Mhm.
for the last 3 years to get us to do more turnkey type solutions. And so, obviously, we build partnerships like from like the motors to the MOSFETs. Like we use mass power semiconductor for the MOSFETs. And then we work through the disties. Like most customers that we're working with, their electronics is new. They used to normally plug in the universal motor, the brush motor right to the wall, and it works. They don't need, maybe the only circuitry that I've seen is they use like a triac dimmer to control the speed on some of the fancy vacuum cleaners. But for the most part, they just plug it in with, and there's a switch and a fuse with a thermal, and that's all the electronics before. But now with brushes DC, there's a level of complexity in the algorithms and also the part selection. So the idea is that if we could bring it all together, and then have a path where they could, get the supplies then that becomes, saves the customer a lot of time, where they don't have to go through all that hurdle. That effectively we give them a kind of, I mean, it's not ready to go to production, but we give them something that now they test within their equipment, they put their application around it, and we've solved all the problems, like where to get the motor, what MOSFETs, where to get the MOSFETs, all that stuff is, we at least give them an option, so they don't have to go through that process of figuring out what to use.
Well, to some extent, that kind of just demonstrates that the types of things at the semiconductor level that you guys are doing what you're good at, so that the designers of the end devices can do what they're good at, right?
Yeah, exactly. Yeah. I mean, they can focus on their end product where they don't have to worry about at least the motor control side of it.
I think that that's going to resonate pretty well with a lot of our audience here, where it seems thankless sometimes, doesn't
Yeah,
it?
yeah. I mean, yeah, sometimes, but I think, I travel all over the world to promote, and I always use this, and I'm hopefully no one will use it, but I guess I'm about to give it. But oftentimes I say, look, I work in Silicon Valley. I have access to all the technology, all the startups, and you see everything that's going around. And sometimes because like I'll get to a point where they're like, we have a, pricing is very important here, or this, there's a certain way we do business here. But when I bring that line up, I say, look, can I show you what I brought? And then they go, sure. And sure enough, when you wow them, because you solved the problem, or it's something that they might have been working on but maybe didn't succeed, but you show them that you got through that hurdle, and not only that, you resolved it, you're giving it to them like ready to, hey, if you want to work with us, here it is. It excites them. I mean, all engineers, we love to learn,
Hmm.
and we want to see how other people, do things, right? And I mean, because nothing ever happens in a vacuum. So I've gotten very lucky with that. As soon as if I put a work, I mean, obviously I got to get management to approve all this work that we've been doing, and there's a lot of other demos, but I don't think we have the time to show you. But we've
Hmm.
done a lot of R&D on our end to kind of position our product above the competition, and that way, we do expect to get a premium price. I mean, this is not about price war for us. Our goal is to enable our customers to be competitive,
Hmm.
to bridge some technology gaps, and also to help them position their solutions in the future, so they can innovate as well.
Absolutely. And you can't expect me to let that just go by. Like I love what you're saying about doesn't happen in a vacuum, and we've been talking
Hmm.
about vacuums for the past hour.
Oh, that's right.
High five for that.
Yeah, I guess that's I couldn't plan it any better, right?
No, it's fantastic. Well, I know we do have quite a few other things that we could go through. Of course, we have several more questions that we could run through. There's a lot in here. There's a lot of interesting stuff that you guys are doing with the control algorithms that we could dig into. But with these last couple of minutes, what are the other things that you wanted to make sure that we include in this tech chat and go?
Well, I mean, we're excited that we recently released this product that's back in April, and we have inventory in our favorite disties. I like Mauser. That's we have not only the some the devices in in stock. I mean, they're modest quantities. Obviously, we don't stock a lot of, but and we also have tools available. Here we're showing our Renesas starter kit, EV kit.
Hmm.
I mean, this was designed by our Japan team, so it uses the ecosystem that our MCU team has been using for the last decade. So we have the Renesas workbench, motor bench. So the boards that I showed you earlier in my demos, those are the ones that we're building ourselves to kind of help our key customers. Eventually, I'm hoping that we'll have these available as well. But for right now, to start, just so you have the full environment. Here you have our device. You have, you can control it through the potentiometer and the switch, so you don't have to use the GUI. But if you wanted to use the GUI, we also have the in-circuit scope circuitry already in the board, so you can just run the motor, get familiar with how to optimize the algorithms to the motor, and then you also have the ability to add, put your own external inverter, like if you need more power. I think these MOSFETs that we're using are 40 volts with about 2 milliohms, so they're pretty powerful. But the kit comes with a tiny little motor. We call it the toy motor. There's no load; it's just a motor. But this is how most people start. You got to have a development tool, and so this is our development tool, and that's also available in Mauser.
Miguel, thank you for this discussion about motor control ICs. I really appreciated the videos showing your products in action. Do you have any last words for our viewers today?
I want to say that thank you for you guys' time. Thank you for your business, and and we're developing more products. Coming out. Hopefully, I could do something very similar with the analog front end that we're going to release by itself, and in the future. But yeah, thank you so much.
That's all we have time for today. Thank you so much, Miguel. This has been bizarrely fun to go through. Thank you so much for your time, and we'll catch you next time. Thanks for being here.
Thank you, Kate, and thank you, everyone.